All right. Good morning, everyone. Let's continue and finish our exercise today. Just a quick roadmap. So we're gonna start and finish the K-means part of the exercise. And then as soon as we do that, we're gonna get into another exercise related to the midterm. Where you're gonna have the chance of making up for some of the grade that you may have missed. So, but that's gonna be on the second part of today's class. Okay, so last class we stopped right here where we ran principal component analysis to address the issue of multicollinearity that we had identified in this data set. We inspected the principal components. We talked about them, how they're formed. We looked into this example of a two-dimensional PCA analysis that is a very simplified version of it. In our case, we have 72 dimensions, so we cannot even grasp that with our human brains. But then we talked about each PC. Remember that each principal component is a linear combination of all the 72 original variables. The number of principal components that we get is the same as the number of the original variables. So we have a total of 72 principal components. From those principal components, we looked into how much variability was explained by each one of them. Always PC1 is going to explain the most variability, and that decreases as the PC number increases. We looked into some of the variables that were impacting PC1. We saw that and we tried to give it some interpretation. So in this case here, PC1 seems to have a lot of the day length variables with a positive impact on PC1, and a lot of the same mean day length variables a negative effect, but then there's a difference there of the months. So we noticed that the colder months, the mean length of the colder months are coming on top here, and then on the flip side of that is the day length of the warmer months, at least here in the US. Again, looking to the variable contribution towards PC1. We're doing this again for PC1 because that is the most important one, will always be on a PC analysis, but it could have inspect any other PC here and looking at what variables would be impacting all the other PCs. So we looked into this plot. This is called a biplot, where we're looking at the eigenvectors, or I'm sorry, the eigenvalues of each one of the variables for each of PC 1 and 2 together. So the longer is this vector here, the more impactful that a given variable is towards both, in this case, both of these PCs. We also look into the same plot, but instead of showing the vectors, we're showing the scores of each one of the observations. So if you remember, we talked about this, that for each PC, we're going to have a formula that would be of the type, the PC1 is going to be, you're going to have all of your 72 variables in the formula, and each one of them is going to have a weight. And then whenever you bring the actual data for each one of your observations, you just plug that into the formula, multiplies by the weight of each one of the variables, and you get a prediction of what would be the score for that observation, for that side here in our case, for that given PC. And then each point here represents that, is one observation of our 698 or something like that in this data set. So two different ways of looking at it. This is more for how variables are impacting PC 1 and 2 and in which direction. This is more to see if we can observe any groupings here. And again, some people use PCA for like determine groupings or clustering. I don't necessarily do that. I think there are better ways of doing it than using PCA. For me, PCA is really a way to decrease dimensionality and also making sure that the PCs are orthogonal. So they're independent, they're not correlated. That to me are the two main properties of PCA that I make use of. Then we did extract the first 4 PCs. We appended that to our previous data set. And then we just ran some quick models here, predicting strength using PCs 1 through 4. We saw here on the output that PC1 and PC4 did not seem to have a strong relationship with strength, but PCs 2 and 3 did. So we went ahead and made those plots. We also checked the variance inflation factor for this model, and this was coming out as 1, and this would be what you would expect. Even if you added all 72 PCs here, they should all have a variance inflation factor of 1 because that's how they come about. They are orthogonal, they are independent, non-correlated. So we just made some plots here to understand. So we plotted PC1 versus strength, which did not have a relationship, which we can observe here. It's a pretty flat relationship. And then PC2 versus strength, which had a positive relationship. So as PC2 scores increase, strength also increased. And with PC3 and strength, it was a negative relationship. And then here's where we stopped. So this was just a very quick review of what we've done up until now. On my side, I do not have any variables in my environment, as I guess we designed this to be, right? Every time we close our studio, we do not save our environment, which is what I would advise you to do. So for me to just keep running, I'm going to keep to the next chunk that I have in the script, which is the first chunk on k-means. Just going to ask to run all above. So it creates the variables for me in my environment. This, again, a reminder, this approach only works if you did not leave any errors lingering in the code above. If you did leave any errors, it's going to try to run, and when it gets to a chunk that has an error, it gives you the error and stops. So I don't know if on your side you're getting this, but I'm getting this behavior here, which I know is coming from the chunk where we asked to print the PMAP. So maybe, oh, I thought it was there. Maybe it isn't. Let me see what. I have a chunk that is creating a long output, and for some reason that long output is remaining in front of me. Maybe it's this one here. Just comment this off so it doesn't happen again. Yeah, I think that was it. Okay, so the second part of this exercise is going to be for us to go through a clustering algorithm. In this case, we're going to be using k-means. K-means is probably one of the most popular clustering algorithms that you're going to find in the literature. It's been widely used. It's still widely used for different applications. And that's why I'm showing you k-means. We're only going to be seeing k-means as our clustering algorithm in this class, but there are many other clustering algorithms as we're going to talk a little bit about in a second here. Okay, so if you all remember, we talked about this distinction here of a model being supervised or unsupervised, right? Really, the difference there is that a supervised algorithm, you give the labels that you're trying to predict to the algorithm, right? So you give a Y variable that has, I mean, and when I say labels, perhaps that's not the best way to refer to it, because labels may make us think of a categorical variable, which could be, but it could also be a numerical variable, right? Like what we've seen up until now, we only worked with numerical variables. And even though those are not necessarily labels in the sense of a categorical variable, you're still given the information that you're trying to predict to the model, right? So I say I want to predict strength with these variables. So strength is the Y variable on the formula. This is a supervised algorithm because you're given the Y variable to the algorithm. On the other side of it, we have unsupervised algorithms when we do not provide the Y variable, right? So PCA was one example of it. We did not provide any Y variable to it. We just gave a whole bunch of X's and said, look for correlations and address them through the principal components. K-means, similarly, is an unsupervised algorithm that is going to create partitions of the group or create partitions of the data set in a number of groups that is called K. So that's why the name is k-means, because K refers to how many groups you're asking for it to look for in your data set. And so again, k-means is unsupervised. You do not provide a wide variable. You just give all these variables and say, look for groupings within this data set. So the way the k-means works, first you probably saw a little bit of this on my other class if you're taking both of them this semester. I'm gonna first say these in words, and then we're gonna see an example of this in action. So the way that k-means works is gonna be so the first step of k-means is gonna be to randomly choose one observation for each k that you're asking for it to create. So let's say I give all this data and I say, give me back 3 groupings of this data set. So let's just take 3 as an example initially. So k-means is going to randomly choose 3 observations from a data set. Again, 3 because I'm asking it to give me 3 groups. Randomly chooses 3 observations from the data and sets those as the center of the groups. After doing that, it calculates the distance of all remaining data points to each one of these centers. It calculates and then assigns a membership. So let's say any observation that is closest to one of those randomly picked observations is going to be assigned to be part of that group. After it does that for all observations and all observations receive a membership, so let's say 1, 2, or 3, then it calculates a new average of the center of that group by taking into account all the observations that were assigned a membership to that cluster. So finds that new center of the group, recalculates the distance of all observations again, assigns each observation to the membership to be the closest to the point that it just calculated, and it keeps doing that process until the mean of the centers do not move anymore. They stabilize, they converge. So I want to show you here that in action, this is a GIF, so it's gonna start over, but I do want to show you here how that works. So this is a very simplified example where we have just like imagine one X and one Y variable. So just 2 variables here that we're clustering over. We can see how, even before you start here, let me see if I can increase so you can see the whole thing. All right. So imagine that we just are giving k-means 2 variables, X and Y. We can clearly see that it seems to be three clusters here, right? That's what it visually seems that there are 3 clusters. You can see on this GIF, the steps on top, starting on 0, going through 12. So on 0, no observations are not assigned to any cluster membership. On step 1, it randomly picks 3 observations because we're asking to create 3 groups. So 3 random observations from the data set, which you can see, like, it's kind of going fast, but if you try to pay attention to step 1, 1 observation was here, 1 was here, 1 was here. Those are the axes that we see there. And so if it finds those observations, calculates the distance of all data points to those 3 centers, assigns a membership to each data point according to the closest center, recalculates the new average of the center based on the observations that fell with that cluster. Then after that, it moves the center of the cluster to a new place, where the axes are going. When it reaches that new place, it recalculates all distances again, assigns a new membership to observations, recalculates average, and keeps doing this until it converges. So until the center of the points or the center of the clusters do not change anymore, which again, in this case, are being shown by the axis here, by the X symbol here. So we see that it starts off kind of not in the right place, because again, the first step is random, right? It's a random selection of 3 starting points. And then it goes through this iterative process where you start seeing the axis move and kind of converge to the actual center of where the cluster centers really look to be, at least visually. Just want to take a quick step here and ask if anyone has any questions or thoughts about what we're seeing here and what I just told you of how k-means work. Yes.
Let's have a question. What if all those groups were like pretty close together?
Yeah, so if the groups were all close together, then it's a matter of, I mean, then I guess we can kind of think of it, are really there any groups in this data, right? Because maybe, I mean, it may be a situation where you don't have like different, like everything belongs to one group, right? Like it wouldn't make sense to partition that further. Then it's more a matter of you learning what is the actual number of groups that exist in this data. In this case here, it's easy to visualize because, it's just 2 dimensions. So it's easy to plot that and have a sense of how many there are just visually, and then just making sure that k-means is able to find that. But in our case, we have the issue of dimensionality, right? So we have 72 variables that we're going to give k-means and ask for it to create clusters for us. So it's going to be really hard for us to visualize that, right? It makes sense to see if it's really making sense, the number of clusters it's finding. So we're going to have to rely on a technique that we're going to see here shortly to how can we use the data to help us determine what is the correct number of groups, right? So that's what we're going to do in the next step here. But that's a great question. So I guess maybe I didn't fully answer it, but let's say that everything looked like it was part of one group, then it would just say like you have one group, you don't have 3, right? Or you don't have more than one. Awesome. Any other questions or thoughts? Right. Okay, so when do we use k-means? So again, k-means you use for clustering, as we're seeing here. It is especially interesting. So anytime we're using clustering is because we have variables that are important for some reason in your research, and you want to group observations that are similar in similar groups, right? And have multiple groups where each group is more consistent within it, but groups are different across themselves, right? So group 1 and 2 are different, but within group 1, observations are very similar. Within group 2, observations are very similar as well. The thing is that we normally don't know how many groups there are, right? And so this is one of the reasons why this is an unsupervised analysis. If I knew how many groups there were and I could tell it what were those groups, it would not be unsupervised. It would be a supervised analysis where I would say, these are the groups, and then I will give all the X variables to say, help me to explain what's going on, how these groups are coming about. In k-means, the premise is that you don't know how many groups you have, but you want to learn that. You want to learn the structure of it. So one time I thought of making this exercise. I have not done it yet, but I just wanted to give an example of how this could be applied in a different setup. So imagine you have your study on the field, or maybe in the greenhouse, or wherever that is, and you know exactly what treatments you apply to each plots. And let's say that your treatments have a very strong effect on your response variable. Let's say on yield. In my case, normally that is nitrogen. So nitrogen rates normally impact yield in a very distinct way that I could at least be able to say, well, I know where's my 0 nitrogen, I know where's my full rate nitrogen, right? They give very different yield levels for the most part. So imagine you have this study on the field, you have all these plots, and then just pretend that for some reason you deleted all of your treatment column information. So you don't know anymore what are the plots that you had on the field, or what were the treatments that you applied to the plots. You just have plot number and yield. That's all you have. And let's say you do know that you had 3 treatments perhaps. So a 0, 50, and 100 kilograms of nitrogen per hectare. So I thought about making this exercise. Again, I did not make it for this time at least. But imagine that you could give the yield data to k-means and say, create 3 clusters for me, because I know that I applied 3 treatments or 3 levels of a treatment. And you could say, based on the yield, look for 3 clusters for me. Assuming that your treatments really had an effect, k-means would most likely give back to you 3 clusters that would relate very closely with, 1 cluster being the 0 nitrogen rates, 1 being the 50, 1 being the 100. So k-means does not know that structure was in place. You know it, but the algorithm doesn't know, but it's able to find those relationships and those similarities in a data set that does not know the labels of. That's kind of like another, I guess, fun way of thinking of clustering. All right, so just a few properties of k-means. So it is used for clustering. It is, again, unsupervised because we do not give it the y variable. We do not give labels. We do not give that information for it. Other way of saying that is that it only takes predictors, so it's only taking x variables in that formula. Those predictors need to be numerical. And also it does not handle NAs. So these are all properties that k-means you need to fulfill for k-means to work. So if you have categorical variables, you can either drop them or do some type of one-hot encoding, which we have not talked about. I don't want to get too much in detail of that and I'll get you confused. So for now, let's just think that we would drop any categorical predictors if we had them. And also does not handle NAs. So you would have to drop NAs on the data set before you gave that data set to k-means. All right, so again, k-means, the reason why I'm showing you k-means is that this is a very popular, one of the most widely used clustering algorithms that you find in the literature. And it is very useful, especially when your clusters are circular, like we saw in the example above. But it can fail badly if clusters have odd shapes or outliers. I want to show you here a figure from a paper that compare multiple algorithms and how in their capacity to create clusters on, I guess, each data set type is a row, each column is a clustering algorithm. The first column here is called mean batch k-means, so that would be similar to what we are using here as far as k-means. And then we have affinity propagation, mean shift, spectral clustering, word, agglomerative clustering, dbScan, Birch, and Gaussian mixture. So these are all different types of clustering algorithms. What we can see here is if we look at the best case scenario, which is this row here of data set, where clusters are very circular, very distinct, and without outliers, k-means does a great job, as everyone else as well. However, if we, now start from the top, if we look at the way the k-means split this data set, we see that it kind of cut right through both of those rings, whereas maybe it would have been better if it had clustered like what we're seeing on spectral clustering or dbScan, which is differentiating the inner and the outer circle. In this other example here, the second data set, k-means is also not doing the best job there because it's kind of mixing those two. Whereas again, spectral clustering, dbScan, and some others are doing an okay job here in finding both of those different shapes. I guess here on the third row, I mean, maybe k-means is not doing a terrible job, but again, some others are doing a better job than k-means. Definitely when we have non-circular shapes or elongated clusters, k-means can also fail badly, whereas some others are better fits for that. And in the last case here, I'm really not sure what would be the best answer because it's just a square with a whole bunch of observations. K-means broke that into 3 clusters this way, whereas other algorithms do a different job here. And I guess just coming back to Anis's question, you can see here that some clustering algorithms just gave the answer was 1 cluster, right? So that could happen. I mean, we have ways of finding what's the best number of clusters for a given data set, but we can see in this case here that it's just returning 1 as the best number of clusters on this specific algorithm here, dbScan. So k-means is popular, widely used. It's not the answer to all of our problems. It has limitations. I just wanted to make you aware of some of those limitations. All right, so one of the things that we talked about when we're running PCA is that you have the option within the PCA function to ask for it to normalize data for you. So we did not normalize our data. We only, I think the only step we did for PCA was keeping numerical variables. In this case here, k-means does not do that by default for you. It does not scale your data. So that's what we're going to do here is just we're going to normalize or scale the data. And again, the reason for that is if you don't, then the algorithm would be more will be more impacted by variables that have a wider magnitude. So if you think of, I think we talked about the example of, I think mean day length was ranging from, I don't know, 40,000 to 50,000 in magnitude, whereas minimum temperature in January was -10 to 10. So variables that have a larger magnitude will have a higher impact if you don't normalize. Maybe you want to allow that to happen for some reason. If a higher magnitude variable is in fact more important and you want to give it more weight, then I guess don't normalize. But in our case here, we want to make sure that all these variables have an equal impact on the outcome. So we're going to normalize them. So if you come here to the next chunk, let's just do that. So previously we created this object called weather_n for the PCA, which is just the weather variables with only the numerical columns that we wanted to give. So only our predictors, only our X variables. And now we're going to normalize all those columns. So let's use a pipe here. So an approach I want to show you here, which is something we used to some extent on when we talked about iteration, is so I want to apply a function that's called scale to all of my 72 columns of this data set. There are different ways of doing that, but we're going to use the function across, which we already seen that function. So let's use well, first we need to call mutate, and then inside this mutate, we call the function across. So here across has two arguments. I mean, they're not called X and Y. I'm just writing them to have a placeholder here. So the first one is almost like a select, where you want to say to the across function, what are the columns you want to apply the function that goes on the Y argument. So here what we want to do is basically apply the function to all columns. So one way we can do that is just call this function everything. So we're saying to all the columns in this data set, so across all the columns of this data set, apply the following function, which is going to be on the Y argument. We give it a tilde. The function we want to apply is called scale. And we need to put a .x here as the placeholder for each one of the columns. So if you run this and you print it, now you're going to see that all of our numerical variables have been scaled. And I want to just expand a little bit on what does that mean. So if we ask for the help, oh, I guess it's already here, the help of this function scale, and we look into the documentation, here's what we learned. So scale is a numeric function that centers and or scales the columns of numeric matrix. If we look at, it has three arguments, X, center. So the function scale has X, which is our data frame or our columns, and it has two other arguments, one for center, one for scale. And whenever you see the formula on usage, if a given argument has a value already, it means that that is the default behavior. So in this case here, the default behavior is center equals to true, scale equals to true. If we read what scale and center, or what center and scale mean, so center here is just basically saying that it's gonna take the, let's see here, the number of columns of X where numeric alike means that as numeric will be applied. Okay, so it's just, maybe it's just applying a mean here, and then scale. I guess it's not really giving us the formula here. Yeah. I don't know, for some reason I thought it was going to give us a formula we could look into. But anyway, so here we're just basically centering is making sure that our variables are centered around 0. So it's basically taking the current value and doing minus the mean of that column. And scale is just making sure that our standard deviation of that column is equal to 1. So a unit standard deviation. So let me just come back here on our code, and we can kind of check that. If we just come here and ask for a summary of weather norm, we can check that all variables, if you look at the mean, all variables are going to have a mean of 0 now. and their standard deviation is going to be around that mean of 0. And you're going to have values that are lower than the mean, so on the negative side, and values that are higher than the mean on the positive side. And this happened for all variables. So now we could see that since everything is centered around 0 and have a standard deviation of units, now these variables become comparable. They don't have different weights. They're not going to impact the outcome of the clustering solely because they have a larger or lower magnitude. So that's what the scale function is doing for us here. I want to close this this output window just because I seem to be getting problems with when I run that. Okay, so all right, we have 72 variables. And I want to, I guess one way that we could create some understanding of how many clusters we have is by looking at our PCs. So I just want to go back to our PC score plot and kind of think about it here. So this one here, if we had to create clusters out of this data, which again is not the data we're giving to k-means, but it represents, let's see, 35 plus 26, so about 61% of the variability of our original variables. And it seems like maybe we would have one distinct here, 2, 3 perhaps, and I don't know how this would look like. Maybe it would be 4, 5, and 6. Maybe we have 6 clusters here. We can try running that first and see what PCA tells us. So I'm just coming back to my PCA chunk. I'm proposing in the text, I'm proposing 2, but we can try 6 and see how that goes. So on this chunk here, let's go ahead and run the k-means function. So the function is really just called k-means. We're going to give here the data set, which is the one that we just created above, called weather norm. So just as a reminder, weather norm has 72 columns, 698 rows, and all the columns have been scaled, which means center and standardized. So k-means, it has this argument for centers. We can say 6, we can try that. And then it has an argument for n start. I want to set it to 10. So I want to talk a little bit about n start and what does that do. So k-means, as you saw, the first step of every k-means, I guess, run of the algorithm is going to pull 3 random, or in this case, 6 random observations, because we have centers equal to 6 random observations from our data set, and have those as the starting centers of the clusters. And then, of course, is going to iterate, try to find the best solution. But the first step is always a random selection of 6 in this case, observations. Because it has the randomness component to it, it could happen that you may, by random chance, select 6 observations that are maybe in a specific place of your 72-dimensional space of your data, that once k-means finishes running the exercise, it may not find you the actual most appropriate center of those clusters. Let's say if your 6 random cluster centers are all clustered on one side of the data distribution, it may be difficult for you to really spread them out in a way that makes sense and find all the proper center clusters or cluster centers. So again, it has this randomness component on that first step. And for us to avoid that we get an answer from k-means that was impacted by the random selection of the initial centers, n start here is just making sure that it runs k-means 10 times. So what I showed you on that GIF from step 0 to 12 was one run, one complete run. So we're asking k-means to do 10 times that, in a way that if you do have, if some of these 10 full runs give you a suboptimal center of the clusters, it's still going to return you the best I guess the best results from across 10 runs. So you don't fall, you don't fall victim, I guess, to the randomness side of that first step if you only run one full run. So it's doing 10 times and returning you the best results across those 10 attempts. All right, so if we just run that here and we print it, this is how the output of k-means is going to look like. So in our case here, we asked it to create 6 clusters, so we'll give back to you 6 clusters, right? So it's telling us here, the first thing it tells us is the size of those clusters. So how many observations fell within each one of the clusters. We see here, you can see the numbers there. There's a very small cluster with only 16 observations. And I guess the largest one here has 207 observations. And then it provides you the cluster means. So what is that? So you can see that it gives you 6 rows, where each one of these 6 rows is for each one of the 6 clusters. And this output here is kind of hard to see because imagine a data frame with 6 rows and 72 columns. This is what it's trying to show you here in this output, because for each of the clusters have a mean value for each of your X variables. So that's what is showing you here, the center on the standardized scale for each one of those clusters. See, all right. So this another part of this output is this clustering vector, which is basically just giving you a vector with the cluster membership of each observation. So this vector here should have 698 observations, which it does, where it has numbers 1 through 6, where that number represents for each of this observation that you gave k-means, what was the membership of each one of those side years. And then it gives us here some more information. So the within cluster sum of the squares by cluster, we can see here what was that sum of the squares for each one of the clusters. And then gives you this ratio of the between sum of the squares. So the between would be the sum of squares difference across clusters, not inside of a cluster, divided by the total sum of squares. So that's basically how much variability of the data set you're explaining with the clusters. So in this case here is about 60%. And then it gives you different pieces of information here as well. All right, so this is just a quick run of k-means. We're not really exploring that a whole lot yet, because I want to talk about, we just, I guess, took a somewhat educated guess of 6 clusters based on our k-means, based on our PCA scores plots. But we can actually ask for k-means, or we have ways to leverage the k-means algorithm and give us what is the best number of k for this data set. So there are different metrics that people use here. One of them would be, I want to show you a couple of them. One of them is the total within cluster sum of squares by the number of k's. So on the algorithm above, we just asked for k-means to run 10 times, but all those 10 times with only a k of 6. Now what we're going to do is have a range of k's, let's say from 1, where everything is grouped as one thing only, to 10, where we would allow it to calculate 10 different clusters for you, and then running all those and giving you how much information you're gaining or how much error you're explaining for each one of those number of clusters. And then we use that plots to determine what would be the best k. So here, we're going to use a function from the package factoextra, which I believe I asked you to install at the beginning of this exercise. Let me just make sure that is correct. Yeah, so Vector Extra was there. You should have installed it. So I expect, and we also loaded it here. So I would expect for you to have that available. So the name of the function is fvis underscore nbclust. So the way that this function works is we're going to give it the data frame, the same that we gave to the k-means function. So the name of the data frame is weather underscore norm. It has this argument for method, and these are things you can explore on the documentation of this function. So the method argument here can take different values. I want to ask it for the WSS method, which is the within sum of squares method. I want to give it a k, so it has an argument called k max, which is where you determine what's the max number of k I want to allow it to compute. I want us to use 10. I think that's normally a good number overall. And then it has this another last argument called fun cluster, which is where you tell it what's the function that you want it to apply to find those clusters. In our case, again, we want k-means. So this is not within quotation marks, it's just the word k-means without parentheses. So just like that. So let's go ahead and run this. So it ran pretty quickly. So this is what we see here on the x-axis. We have the number of clusters we're asking for the algorithm to calculate. Again, going from 1 to 10. This is normally enough, but if you wanted to extend that to more than 10, you can just change the argument on the function above. And then it's showing you the total within sum of the squares for each one of the case that you have on the x-axis. So this, you may have also heard about this plot being referred to as the elbow method. So this is one other way of referring to this, this algorithm, which is basically the goal here is that we choose a number of k where you see an elbow. For our data sets, you know, that elbow, I guess you could say it may start at number of k equals to 3. I guess anywhere between 3 and 6 would be a good guess for the best number of clusters if we're just visually assessing that. Perhaps 3 and 5, I would say, more closely. But it's really where that elbow happens. So where that break point almost is happening on this data set, because we do want to choose the number of clusters that after which you don't gain as much information if you add extra clusters. And we just, normally our goal here is to find the minimum number of clusters that explain the most information, right? So there is a trade-off here. If you keep adding too many more clusters, imagine, well, let me take one step back here. If we think of the extremes, on the lower side of things, the extreme would be to say, all this data should be just one cluster, meaning that I guess you don't really learn much from it that way. But you can just say all this data set is just one cluster. Kind of what Anis was saying is if your data does not have groupings, maybe one cluster is the answer. However, on the other extreme of this, we could ask it to create 698 clusters. That would mean that each cluster has one observation only, right? So those are the extremes that we're working with in our data set. Our goal here is to find something hopefully more than one and hopefully a lot less than 698 that we can create a limited number of clusters that are very similar within the observations inside the clusters are very similar, but they're very different across different clusters. That's our goal here. And that's what this plot is helping us to achieve, is to find that break point where, okay, if I keep adding more clusters after a certain point, I don't gain that much more information. That's what we're targeting here. So again, I guess for this case, I would say probably somewhere between 3 and 5 seems to be the best approach. So this is one metric that we can use. Again, the total within sum of the squares by number of clusters, and also called the elbow method. There's another method I want to show you here, which is the silhouette width. So if we just run this, again, everything is the same as before. The only difference is I'm changing the method to be equals to S, which stands for silhouette silhouette width. So on the silhouette width, what we are looking for here is that, so it's increasing again the number of clusters on the x-axis, and is giving you the average silhouette width for each one of those clusters. We want this average width to be highest as possible, because it means that your observations in that cluster have a larger level of similarity within the cluster. So that's basically what silhouette width is doing for us. Is another very popular metric to select number of clusters. And in this case here, because it's really easy to say I want the maximum silhouette width, the algorithm gives you a recommendation. So it's recommending us to have a silhouette width of 4, or sorry, is recommending us to have a number of clusters of 4, which matches with the highest silhouette width within the number of Ks that we created. So I guess in our case here, if we use both of these metrics, if we think of the total error, probably I would have chosen somewhere between 3 and 5 as where the elbow of this is. Silhouette width is recommending 4. So they're, to some extent agreeing around the number of K to be equal to 4. So maybe let's just go ahead and do that and assume that our data set has 4 clusters. If you come here on the next chunk, we're going to rerun the k-means algorithm as before, but with the difference of specifying centers equal to 4. Is there any way we can use this method of choosing k, but not assessing visually and feeding best k directly to k-means clustering function? Okay, let me think about it, Sikar. So Sikar is asking if there's a way to automate, I guess, the selection of K. Not that I know of. I don't know. I don't think that the k-means algorithm itself has that self-learning property. But I mean, you can always, if you, I guess the function here, the question is, can we automate that to an extent? I guess the way the algorithm was developed, the k-means algorithm was developed, it does not give you that option. But if you wanted to automate this yourself, you can create your custom function, right? So you can create a function where you say, I don't know, find best k or something, where you kind of just plug in these algorithms together, and then they make a selection for you, and they feed that selection right into the k-means algorithm, and that spits out the outcome of that. So I don't think there is natively, but it's not something that would be too hard to create your custom function to have that done. All right, so let's go ahead now and run, I guess, our final k-means, which is going to be the one with the proper number of k that we just found out before for our data set. So let's call k-means again. We give again our data set weather underscore norm. We're going to say use the centers argument and say centers equals to 4 as we just obtained the number above. And then make sure that you ask for n start equals to 10. So if you go ahead and run that and we print it, it's going to be a very similar print as we had before, except that now we have 4 clusters rather than 6. So we only have, so here's given the number of observations per cluster again. Is giving the mean for each cluster across each one of our variables that we gave for the clustering algorithm as well here. And if you just keep scrolling, you're going to find that it gives you that vector of cluster membership that again now only has values 1 through 4, right? Before we have 1 through 6, now it's just 1 through 4. And we see here that this ratio of between sum of the squares and total has decreased to 48.2%. This is very common, that the larger number of k you allow the algorithm to find for you, the higher will be this proportion. But again, we're only going to have 100% here if we have 628 clusters, which again is not the goal, right? We're trying to find these overall patterns, but not to fully explain everything that's going on in the data set. All right, so let's explore our clusters a little bit more. I guess it already gave us that information above how many observations per cluster, but I just want to explore this as well and see how could we learn how many observations we had if we did not have that output. So let's start here with our weather data set. So this is not even the one that we gave to k-means, but at this point, I just want to know how many observations fell within each one of the clusters. So this is going to work. All right, we're going to need a mutate here, but I want to stop for a quick moment and ask, what do I need in this weather data set to be able to calculate the number of observations per cluster? What column I need here? Say that again?
Daily.
Well, day length was one of the variables we use for clustering, but think of like, if I want to know how many observations are there in a given cluster. Okay. Say that again? What do you mean by that? Yeah, so Pramod got it. So if I want to know how many observations I have in each one of the clusters, I need to have a column that tells me what was the cluster ID of each one of the observations in my data set, right? So yeah, we need a column here that is the cluster ID, which we don't have yet. So that's what we're going to create here on this mutate. I want to call that cluster. And this is going to be a vector coming from that k-means model fit. So the k-means model fit, we assign that to an object called mod underscore km4. If you use a $sign here, it has this vector in it that's called cluster. If I just run that, just so you can see what that is basically that vector of the cluster ID membership as the outcome, right? So if I do this, I mean, we would have to go all the way to the right here, which is going to take me a moment, or maybe I can just do a select just to show you. You don't have to do the select. I just want to show you. So let's select ears, sites, and cluster, just so we can more easily visualize that. So now each site ear has a cluster ID, right? So now I know exactly what cluster did each of my environments belong to in the end. So I'm going to, I guess, delete this dplyr. I'm just doing that to make it easier for us to see. Okay, so, all right, so now we do have this column that is cluster. If I want to know how many observations I have per cluster, what do I need to say here? Okay, summarize is going to be there, but we have to group by first, right? So let's do a group by on the cluster, and then we're going to summarize. So I want to show you here a shortcut perhaps. So we could ask here to summarize and ask for the length of each one of these clusters, which would give us the number of observations. If you're doing summarize specifically to get the number of observations in the grouping variable, in this case cluster, there's another function that is a shortcut for that. It's called tally. So I can just ask for a tally for each one of the clusters, which gives me the length of each one of them. So how many observations are there within each one of them? So again, we already have this output here on the print of the k-means model object, but I still wanted to show you another example of a quick wrangling that we could do to learn that ourselves in case that was not provided. So again, we see here that cluster 1 has the most observations. Cluster 2 is very small, which is interesting because, you know, is it even worth it having a cluster with so few observations? I guess the algorithm told us it was, so we can keep it for now, but it's just something that is useful for us to think as well. All right, so, you know, for us now to visually inspect the results here, which I always recommend, like every time you're doing anything with data, you need to visualize your results. Just looking at tables and numbers themselves can give you the wrong impression. So for us, again, to visualize the results, we can either add that cluster column to our original data set like we did above, right? So we added that resulting cluster ID to the data set. We did not assign this to an object, so we didn't save this, but we could do that again. And explore the distribution of each one of those variables against cluster ID. Or we can use a function that summarizes all the information of the original variables for us into PCs and plots the cluster ID. In this case, because we have so many variables, 72 X variables, I think it would be, a little bit harder for us to really make sense of what is going on across all those 72 variables. We could still do that. And I want to show you here one way that we could attain that. So I left you the code where we're starting with the weather data. We're again adding here the cluster ID, and I'm turning that into a factor. Then I'm pivoting longer everything except year, site, and cluster. And then we're creating box plots of all these variables. This is going to be, as you would imagine, we're going to have 72 plots here. So it's going to be a lot of plots. That may take a moment to run. So I created all these plots that on the output right here, it doesn't even look that good. I just want to export this using DigiSave, which I left you the code there to do. And I just want to go on the output and quickly check our cluster validation figure. So again, it is a very long figure because it's a plot for each one of the variables that we gave k-means. And just, I guess visually assessing here, we can see that some clusters are potentially similar for given variables. So let's say if we think of cluster 2 or 3 and 4 in this case here, they're similar when it comes down to Tmax in August, but they are potentially different in other variables, right? So if this is the mean solar radiation in May, it seems like clusters 3 and 4 are different. So this is kind of one way that we could use to validate these and try to understand which variables here are creating, or which variables can we actually, of the ones that we gave k-means, which variables can differentiate different clusters in different ways, right? This would be one visual way of assessing that. So I don't want to spend a lot of time here, but I just wanted to show you that that would be one example. So another thing that we could also do is, which I don't think we're going to do in code, but we have done in a previous exercise, was another way that we could explore this would be to run the analysis of variance that we're kind of seeing already in these box plots. So if you think of like any of these box plots here, we could do an analysis of variance where we have the weather variable as the Y variable, and then cluster ID as the X variable. So we just run analysis of variance. Or I'm sorry, cluster ID. No, that's correct. The weather variable as the Y in the analysis of variance model, and then cluster ID as the X variable. That's what would basically create this box plot, but then actually run this analysis and compare the means, right? So a model like that could be run for each one of the 72 variables here in a way that we could then add letters and make some inference about whether they're similar or different for each one of the weather variables. So something that will look like this, right? So we have variable explained by cluster. So as an example, mean day length in January explained by cluster ID. And then you could extract the means, do pairwise comparisons, and plot those letters as we've done before. I think we've done before in this class. Have we? Someone that's only taking this class, have we? So I'm kind of confused about both classes I teach, and I don't remember if we actually done that in this class. Have we ever done like maybe on the iteration exercise? I think we've done the running analysis of variance and adding letters to multiple box plots. Maybe we have not. Anyways, but we could do this, doing a pivot longer, group by variable, like group by the name of the variable, nesting, and then doing a model pairwise comparison, CLD and then making a plot using the mapping list approach. Yeah, so we could do that way if we wish to add letters to these box plots. So I'm not showing you how to do that here, but that could be one way that we could use to explore that. Okay, I do want to show you a different way that we can explore these. So if we there is a function from the Facto Extra package that's called, if you want to type with me, @this_cluster, which is used for a similar purpose of what we're trying to do. So here, what we're going to do is give the k-means model that we created. So that's the mod_km4. And then we need to say where this is coming from. So data equals to weather_norm. If you run that, I just want to call your attention to what's happening here. So notice what we did. We imagine that you were running this function in a completely different script where you did not even look into PCA. This function by itself, we're just giving our k-means output and our data. We're not giving anything related to PCA to it. Behind the scenes, it is running PCA for you, which we have already done in this exercise, but it's independent of that. It is running, this function is running PCA for you, putting your x-axis on, or your PC1 on the x-axis, PC2 on the y-axis, same as we've seen before, getting you the PC scores, which we saw here. So it's making this plot for you, which originally we created based on the PCA, but that function all the way down there is making that plot for you, and then giving colors and creating an ellipse around each one of your clusters for you to be more easily visualized, right? So remember, PCA is giving you the PC1 and 2 across all of your 72 features, which is doing behind the scenes for you, and then coloring and creating ellipses around each one of the clusters that came from k-means. So it's kind of combining both into one thing. Very easy, right? I mean, think of it, you just did PCA unintentionally, I guess, or maybe unexplicitly with this function and made a plot that's already grouping things for you. So again, here, if we were to look at this plot, we would see here, so the small cluster that we originally observed in our PC scores when we did PCA was indeed turned into one cluster. And then everything else was separated into 3 clusters, and we were seeing them here. I guess Neva had a question last time that was a really good question as far as, okay, we're talking about multicollinearity. We talked about how PCA helps us to address multicollinearity. And now we're going to do k-means without using the PCs, but only using the variables which are multicollinear. Could that be an issue? So I guess my answer back then to you was, I didn't think it would be an issue. I read some papers, I went after it. It seems like it could be an issue sometimes, but not always. And I guess on this case here, so let me take one step back. If we thought that multicollinearity could be an issue for k-means and we wanted to address that right from the beginning, what we could have done is to run k-means, get the PC scores as we did, extract the PC scores for, let's say, the first 4, 5, 10 PCs. And instead of giving the weather variables to k-means, we give the PC scores themselves, which is what we did on this exercise here. So we got the PCs, and then we got the PC scores for all observations for the first PCs, and we appended that to our original data set, and then we ran linear models of strength explained by PCs. So we did that here. What we did not do was we did not feed the PCs into k-means. We fed the original variables, which were multicollinear, whereas the PCs are not. So we could have done that, right? And instead of coming here to k-means, instead of giving here the original variables, we could have given the PCs themselves instead, which would have addressed the multicollinearity problem. In this specific data set, and this plot is it's still running k-means with the data, but is showing the visualization based on the PCs, just to facilitate us visualizing 72 dimensions. So it seems like for this case, if we would have done that, if we would have given the PCs instead of the variables, I would imagine it would still find similar groupings, right? I guess if we plot the PCs and the k-means that were based on the original variables, and so not PCs, and we saw groupings on the PC plots that did not make sense visually on the two-dimensional space, maybe I would think, okay, there's something going on here, right? So maybe let's say that this one was grouped like this. Let's say if this green was grouped like that in this two-dimensional PC space, maybe we would have suffered from multicollinearity. But in this case, it is applying PC on the original variables and just grouping them and coloring them by clusters, which came from k-means, which gave the original variables. And the clusters still look very compact. I would say we did not have that issue here. But it doesn't mean we would never have that issue, right? So let's say if you do this, and on the PC plots that we're seeing, your k-mean clusters look weird, look disconnected, maybe that would mean that you had some issue of multicollinearity. Perhaps it would have been better to have given the k-means algorithm the PCs instead of the original variables. Does that help to? No? Too many words all at once? Well, it's recorded, so.
Say that for the multicollinearity, it might be useful to use those box plots. So you choose, let's say you have different clusters, and within one cluster you have like 3 variables that are significant. For that one, you just choose one of those.
Yeah.
So 1 or 2 for each cluster.
Yeah, we could do that. Yeah. So Jonathan here is saying that we could have used this plot here to look into variables that had a similar behavior on the box plots and only choose one of them. We could do that. That's definitely a way as well. Another thing that we could have done, and I think we talked a little bit about this, was we could have used or not necessarily this plot, but the information behind this plot and look into clusters of variables that are highly correlated and say, well, I see all these variables here are highly correlated. I'm just going to pick one of the pair and remove the other. We could also do that, I guess, by hand would also be an option that I guess it would address what you're saying as well. Yeah, so different ways we could do that by hand. But in this case here, I don't think multicollinearity impacted the k-means, which again was done on the original variables. I don't think that was an issue based on this plot that we're seeing. Okay, so in summary, in this exercise, we covered when multivariate analysis can be used. So we talked about different types of multivariate and some examples of them. We did show that multicollinearity can be an issue when you're running linear models, that when you're given all these variables at once to a model, you could have issues of getting your coefficients of the regression model to change in direction, in magnitude, and even have the standard errors inflated. We saw how to use principal component analysis for dimensionality reduction, and also for creating the PCs, which are orthogonal, so are independent. They are not correlated with each other. Then we use k-means for clustering. So again, when you have all this data and you want to see if there is a pattern as far as can you group observations alike into groups, k-means one example of that. We saw the k-means is not a silver bullet. It does not work perfectly for every situation, but it is the most popular algorithm that you're going to run across. And then we saw a couple ways to how to validate the results from both of those analyses, which is always important, right? We always want to learn, understand what these algorithms are telling you at the end of the day, and really know which variables are driving them, how is that impacting your results. All right, any questions? So make sure you save your script, make sure you do a git stage. So in your git panel, make sure you stage, commit, and push. finished multivar. And push, so it goes to your GitHub repos. Okay, so here's what I want to do next. I know we're gonna start with the exercise for you to have the potential of making up for some of the grade that you missed on the midterm. I will tell you what I want from you. And then if you want to take a 5-minute break after that, you're welcome to. If you don't want to take a break, you just want to keep going and use the most time, which we have until 11:30, you're welcome to stay and not take a break as well. So here's what I want you to do. You're gonna go on ELC. I think you all may have already seen that you can see which questions you miss points, right? If you go on ELC, go on the quiz, you can check on that. So what I want you to do is you come on, it could be this project, could be any RStudio window, doesn't really matter. I want you to come here, create a Quarto document. We can just give a title of, I don't know, midterm makeup. So every time I create a Quarto, it gives you the visual editor, which some people may like. I actually prefer to use the source view. So I just flip to source by clicking that button. And I just delete this part here of the YAML editor visual. I just delete that. I normally delete everything afterwards and I start fresh. So what I want you to tell me here is, so your name. And then the question that I want you to answer is the following. So I want you to tell me, why was my original answer wrong? And answer again. For each question that you missed, I want you to answer these 2 points. So you're not only gonna tell me what is your new answer to try to make up for points, but I want you to tell me why was your original answer wrong. If you don't answer both of these things, so for you to be able to make up the points for any question you may have missed, you have to answer these 2 things appropriately. If you tell me why you missed, but you give me the wrong answer the second time, you don't make up points. If you give me the right answer, but you did not understand why you missed the first time, you do not make for any points either. So what I want you to do on this script here, again, is tell me your name. Keep in mind both of these questions. What I want you to do then is you can just do something like 1, where you're gonna copy from ELC the question that you missed. So let's say you go there, copy the whole question, not the answer, but the question. Paste that here, and then address both of these points. Go to the next question, put the question name here, paste the question name from ELC here, and answer again, why was your original answer wrong? What is your new answer? Okay, do that for each one of them. Any type of question, it could be true or false, all the way to the ones that you had to explain a process. I want you to do this. You're gonna have until 11:30 to do this. Once you're done, make sure you do save this Quarto here to really anywhere. I don't care where you save it. You could be to this code folder, that all the multivar. Just make sure you save it. I want you to give it the name midterm makeup dash your first and last name. And then you can send me your QMD. You don't have to render it. You can send me your QMD by 11:30. I want to be very clear. 11:31, I do not accept anything else. If you send me, I'm not going to grade it. 11:30 is the cutoff. Send me your answers by 11:30. Only try to, again, make up for the questions that you missed points, which are the ones you can see on ELC. And that's it. If you want to take a 5-minute break, feel free. Oh, and also, I guess I forgot to say, you can use your material. You can use your notes, you can use code, you can use your lectures for this. You cannot talk
question,
to
Dr.
colleagues.
Bastos.
It is individual still, but you can use your own material. So if you need a break, go for it.
Quick question, Dr. Bastos.
Yes.
So what if, and this is not like, being funny or smart or anything, this is genuine. What if like for what we didn't know why we got the question wrong? What if we just genuinely didn't know that answer? Like, is that an acceptable answer for why was my original answer wrong? I just was not like I didn't know. Like, can you be like a little more specific on that?
Well, so
What's an acceptable answer?
I don't really want to know, like, so my question is more, why did you miss, like, why was your answer wrong? So even if you didn't know at the time, I hope that you can learn now. Right? So let's say if you said something was true and it was actually false, you have to tell me why was that, like, why did saying that it was true was wrong? Like, why is this false, I guess, would be the way to approach it. So even if you didn't know at the time, I hope that now you can tell me why your selection was wrong based on your knowledge that you can go through your material.
Yes, sir. Thank you.
Yeah. All right.